Hi, everyone, and welcome to Astro at Home, presented by Discover the Universe. My name is Lindsay Mann, and I work for Discover the Universe, where we normally teach your teachers, but right now, while we're all learning from home, we're happy to be coming into your homes to teach you about astronomy. Before I introduce our speaker for today, I want to remind you guys about our chat policies. So we're very excited and happy to receive questions from you in the chat. We ask that you remain respectful and refrain from spamming, which means sending multiple messages at once. So without further ado, I'd like to introduce you to Mary Beth Laychak. She has presented with us before. Today, she's talking about the telescope where she works, the Canada, France, Hawaii telescope in Hawaii. So Mary Beth, welcome. I'm going to hand over to you.
Hi, thanks, Lindsay. You guys can see me and everything like that?
Yep, all's good.
Awesome. So thank you so much for joining today. When I talked before about when I've done my previous presentations, I had a lot of questions about telescopes and how do they work and why are we in Hawaii? So today I wanted to talk a little bit about all of those questions. So I work at the Canada, France, Hawaii telescope. It's called CFHT. This slide says outreach manager because I forgot to change it. My position is actually called the director of strategic communications. And so my job is to explain astronomy to people. Now, last year in 2019, CFHT celebrated our 40th anniversary. And so we had a special logo here. I have it in French, just as a nod to the fact that we speak both English and French in Canada. All right, so who is CFHT? So as I said, we're the Canada, France, Hawaii telescope. We're a 3.6 meter telescope on the summit of Mauna Kea. And Mauna Kea is something that we're gonna talk about in a couple of minutes. It's a 4,200 meter or 14,000 foot dormant volcano on the Big Island in Hawaii. We're a joint partnership of the National Research Council of Canada, which is like the National Science Foundation for any Americans that are watching, CNRS, which is the French equivalent, and the University of Hawaii. We also have partnerships with Taiwan and China, which means they can use our telescope as well. Our headquarters are located in Waimea on Hawaii Island. And so if you look at my map there of the state of Hawaii, the little orange island, or I guess the big orange island, is Hawaii Island, known as the Big Island. And then when you zoom in just to looking at the Big Island, that red patch is Waimea, where our offices are located. As I mentioned, we're a 40-year-old telescope. So this is what our telescope looked like in 1979. What I really love about this picture is you can see snow and that we're completely above the clouds. So because of the high elevation of Mauna Kea, it does snow from time to time. We actually had a really light dusting last week. Now, the temperature doesn't change a lot over the course of the year. A warm day on Mauna Kea is about 10 Celsius. That's roughly 52 Fahrenheit. A cold day would be right around freezing. Last winter, we did get down to about 10 degrees Fahrenheit, which is minus something Celsius. So it can get pretty cold. We get most of our snow in the winter, not because the temperature is that different, but just because of where we're located in the Pacific. We end up having two seasons in Hawaii, the dry season and the wet season. The wet season is wintertime. So when we have the wetter air in the winter, that ends up being snow on the mountain. And as you notice, we are floating above the clouds. Those clouds are going to be really important to talk about in a couple of minutes. So we'll wait. This is what we look like today. Now, I have my coworker, Greg, in this image for scale. He's the guy on the catwalk. He is not usually staring, pensively out into sunset. What he's doing in this image is actually standing there for scale so that you can see how large the telescope is or the size of the building. One difference, if you notice from this picture to this picture, are these vents here. I hope you can see my arrow. They work like louver windows in your house. We were noticing that when the dome was open, and so when we want to open the dome, there's a slit right here. And what we were noticing is that all of the hot air rises in the center. Now, we all know that. But what was happening was when we were looking at the sky right above the top of the telescope, we were looking through a funnel, a channel, a chimney of really warm air for the first couple of hours of the night. So what we did was cut holes in our dome and installed basically windows. And when we're using these louvers, we open up the louvers and it flushes the air out of the dome, which brings the temperature in the dome down. So I see a couple questions here. Do I live in Hawaii? Yes. I live about a mile from our offices in Waimea. So we have a telescope at the summit and then about an hour and a half drive from the telescope are our headquarters in the town of Waimea. Does the snow interfere with the telescope? It's sort of. So the snow interferes with the telescope when it's snowing. So if it's snowing, if it's raining, if it's way too windy, we can get winds that are up to over 100 miles an hour. And so when any bad weather's coming through, we can't observe. When the snow is just laying on the ground all nice and pretty and sunny like it is in this image, it doesn't impact our observing at all. All right, so why Mauna Kea? Why 40 years ago did a bunch of Canadians and Frenchmen and people from the University of Hawaii decide, hey, let's build a telescope in Hawaii? Put quite simply, it's the best site in the world for astronomy. Now, you may hear other people who give talks are going to say that Chile's the best place. There are definitely pros and cons to each site. In Chile, the weather's clearer a little bit more often, but the best day on Mauna Kea, I would argue, is the best day in the entire world, the best place in the entire world. One of the things that I want to point out is the spelling of the mountain. So sometimes you may end up seeing this as two words, M-A-U-N-A space K-E-A. So Mauna is the Hawaiian word for mountain and Kea means white. So there are two different groups of Hawaiian studies in the state. So we've got people who work at the University of Hawaii in Honolulu and people who work in the University of Hawaii in Hilo. Hilo's on the Big Island, so you can kind of think of that as the people that the observatories work the most with. They prefer the one-word spelling because it is a specific white mountain. They argue that any mountain that would be a white mountain would be Mauna Kea with two words. It's actually really super complicated, but we've just decided that since we're on the Big Island, we go with the way that it's spelled culturally on the Big Island. So back to why we're on this mountain. It has a really dry atmosphere above it. So even though I said it snowed and I showed you the pretty snow pictures, we have about probably 300 nights a year where it doesn't snow and we have super dry atmosphere. Like right now, if you would go to the summit, the humidity, I think last night was around 10%. It's craziness. It's usually cloud-free. Like I mentioned, we have about 300 nights out of the year with no clouds. The atmosphere above it is super stable. And the reason that it's super stable is we're not near any land. So if you look on a map, and I want you guys to all try to look at a map of the Earth, and you see Hawaii, we have nothing around us, which means that the atmosphere above us is super stable. We don't get any sort of roil or boil in the clouds above us. And so anything that interferes with the light coming from space and hitting the telescope, so if that is hot air, if that's turbulent air, all of that causes our light to get the light that's coming to the telescope to wiggle a little bit, twinkle. We all see this with our eyeballs. When you see stars twinkling, the higher you go, the warmer the air, the more your stars twinkle. And so if you ever look and see, like, look at the stars on a really turbulent night where there's going to be like thunderstorms or high wind, you'll notice the stars twinkle more. And so that's why the hot air, we want the hot air to leave our dome. The warmer the air, the more the light twinkles, the more the star twinkles, okay? And the higher you are above the Earth's atmosphere, above the Earth's surface, the less air you're looking for. So if you're at a higher elevation, your stars have less twinkle in them. There's very few city lights. I think the population of the Big Island is around 200,000 people in an area that's really big. So we don't actually have a lot of light pollution. So we have really super dark skies, and I'm going to show you what that means in a minute. So the atmosphere at the summit is dry, it's pure, and it's clean with no pollutants, thanks to the inversion layer. So a couple slides ago, when I showed you that picture of the telescope, we could see the telescope, the beautiful summit, and then what looked like a layer of clouds. I always think that those clouds look like there's something that I could jump into, and it's so fluffy that it would support me. Now, obviously, you can't do that. You can't jump on the clouds. But those clouds are what we call the inversion layer. And that's where the cool, dry air of the atmosphere above us meets the warm, dirty, wet air, the humid air of the atmosphere below us. And it forms a cloud layer. Because it's below the summit, most of the time it keeps the summit really, really, really dry. It also keeps all of the ick in the atmosphere below the summit. Now, in a lot of places, that ick in the atmosphere would be due to pollution from cars or people. On the Big Island, we had an active volcano named Kilauea that was exploding, erupting for about 30 some years. And so a lot of the ick in our atmosphere was due to the volcanic eruption. It was called VOG. Now that stopped erupting about a year and a half ago. So right now the air in the Big Island is the cleanest it's ever been. Now, this is a picture of Mauna Kea. You can see of the sky from Mauna Kea. The really bright patch over here is actually the moon. And so this is the Milky Way. The galaxy that we live in is the Milky Way. And what we're looking at here is one of the arms, one of the spiral arms of that Milky Way. Mauna Kea, they've measured how dark it is, and it's one of the darkest places in the entire Earth. And I wanted to give a shout out here to Peyton Todd. She's was a high school student when she took this photo, and she lets me use it in my presentations. So why CFHT? This is a picture of our actual telescope. Here, this is Tom, again for scale. We are orange and brown. Yellow and brown. We don't actually see telescopes that look like this anymore. We're what you're called an equatorial mount telescope. And so the brown part, I have a video here that shows you how the telescope moves in a couple of slides. So this is what we look like. We have a lot of extra space in our dome, which means that we're not super cramped. 40 years ago, they really built things quite big. All right, so this is our mirror size compared to other telescopes. We're a medium-sized mirror, and the mirror is the most important part of a telescope. The light from space comes in, reflects off the mirror, and then bounces up to what we call the secondary mirror, or the upper end of the telescope. And I'll explain more about that in a couple of minutes. So this is a video of us getting ready for the night. So you'll see here, this is the shutter opening. It's actually super loud. This is a time-lapse video, so there's no sound. It works just like a garage door. And so the shutter opens at the beginning of the night, and this allows us, this is our window. This allows us to look out and see space. Now, once the shutters open, we're actually going to see our dome spin. And so the dome is the walls of the telescope, or the walls of the building here. It's one of the craziest things. If you're standing on the dome, like right here, we have a catwalk that allows you to stand there, and the dome's moving like it is in this picture. You feel like the telescope is spinning. You'll also notice on the sides here, those louver windows opened up. They popped open. And as they continue to open, we'll see sunlight entering the dome. Now, at the start of the night, we always turn the dome to the east, which takes it away from the setting sun. And then this is our telescope moving. Right here is our mirror. So what happens again is the light from space comes in this way. It reflects off this mirror and it bounces up. Now, right now we have a camera on here. It's called Megacam, and we'll talk more about Megacam in a minute. It's called Megacam, and that camera is a digital camera that takes a picture of space. Now, if we want to, we can also hang a camera on the bottom of the telescope. To do that, the light from space comes in. We put a second mirror here. The light hits the secondary mirror and bounces back, and you'll see a black, what looks like paper towel tube here. The light would go back through the paper towel tube to the instrument hanging on the bottom. Now, any questions on how the telescope works? Lindsay's sending me questions. So do the volcanic gases interfere with the telescopes? Sometimes they did. Now, most of the time that inversion layer kept all of that ick below, but in 2018, we had a really big eruption on the Big Island. Some of you may remember having seen that on TV. It was pretty crazy. It was about 90 miles from where I live, so I was fine. When that happened, we would occasionally see plumes of gas and dust kind of breaking through the inversion layer, but most nights, just because of how high Mauna Kea, it doesn't bother me. We get to the telescope by driving. So there is a road. You drive from Waimea to a 3,000 meter level. And there's a place there called Halipuaku. And that's where the astronomers, it's their residence. That's where they eat breakfast. If you're technical staff, so if you're an engineer or a technician, you hang out there for about a half an hour in the morning eating breakfast. It's really dangerous to go straight up to the telescope because you're going from basically sea level to 4,200 meters. And so that's really high. There's a lot less air. You're at 60% atmosphere, which means that you have 60% as much air as you do on the summit. And so you get really short of breath really quickly. So you have to acclimatize slowly. Great question. How far can